Dos, tres, cuatro.
Hi class, today we're going to take a look at hyperbolas, the last section in our conics unit. And here's an example of a hyperbola. So we'll just start off right off the top, where you can see that it almost looks like if you were to have an ellipse and you were to break it apart, and rather than the two halves of the ellipse connecting together, they split apart. Something like that's happening, but then there's other characteristics on top of that. So there's a few terms that we're going to have to learn today. The first thing before we get started with anything else is there's two types of hyperbolas. One type of hyperbola begins with something in which you would open, I guess, we're going to go up and down forever. And if you have something like that, then that's going to take on the form of what we would call x squared minus y squared equals 1. And that's going to be different from when you have a hyperbola that is going to go left and right forever. And if you have something like that, that would take on the form of y squared minus x squared equals 1. Now, if you wanted to, you could potentially say x squared minus y squared equals -1. We won't in this class, and we won't in Michelson, but just know that that would be an equivalent form of that as well. So a couple terms we just want to run you by before we get really into this is regardless of which type of hyperbola you have, the two parts right here, those would be your vertices. And so you're going to have two vertices for every hyperbola, and that's joining the axis that goes from vertice to vertice with the name of the transverse axis. So basically the transverse axis is going to represent wherever the vertices connect with each others. And if you take a look at our definition right here, transverse axis says that it's the axis that runs through the vertices. Running perpendicular to the transverse axis would be the conjugate axis. And every hyperbola will have a transverse axis and a conjugate axis. You can see here that we have some asymptotes, and we'll start to develop how that plays into our hyperbolas and our hyperbolic behavior. And then finally, your favorites, we do have a couple of focus points, and we'll see how we can use that to be able to find out more about hyperbolas. Now, when we take a look at our two cases of hyperbolas, I don't know if this is gimmicky or not, but I often think that this first one right here, it actually kind of looks like, when math teachers write x's, they write them like that. It almost kind of looks like if you're to split that apart, and it would be kind of like this. Why am I doing that? If you could have something like here and like here or something like that. So if you want a sort of a gimmicky way to memorize something, you could say that the x squared starts in this form because it looks like an x being split apart. Maybe this one here looks a little bit more like a y or something like that. And that's why it begins with the letter y. Okay, I don't know if that one helps or not. Okay, so let's see what we could have with something like this. Now, if you wanted to, we could isolate for y right here. We see that it's in the form of x squared minus y squared, and so we would have something in which probably it's going to look like that. But if we wanted to algebraically isolate for y, we could do that as well, and you could get something in which you could say -y squared equals 16 minus x squared. Y squared is equal to x squared minus 16. Square root it, and y would be equal to plus or minus the square root of x squared minus 16. And you could start to input some numbers in here very quickly then to be able to figure out what would happen with the behavior when you start putting in some numbers for x and some very large extreme numbers for x. So I've done this ahead of time just so I can help fill this in a little bit, but you would get these points right here. So you begin by getting the point 40 and negative 40, and those would be our two vertices. But then as you start to fill in a little bit more, you would see, well, okay, so now I'm at the point 5,3 and negative 5,3. And then I'd be at the point 6 root 20 or negative 6 root 20. And this is approximately 4.5. And when I put in 7, I get root 33 and root 33. And that would be approximately 5.7. So we should start to notice that hopefully you're seeing that your y values are starting to get closer and closer to your x values. Well, if you start putting in large numbers like 100, your y value turns out to be 99.9. It's like 99.91 something or something like that. And then if you put in 1,000, you get 999.9. And if you put in 10,000, you get 9,999.9, and so on and so on. And so hopefully you guys know where I'm going with this. And so what you could start to say then is that there's clearly some form of asymptote-like behavior because you're getting so close to this value, but you don't quite reach there. You could graph something like this on Desmos, and if you were to look at it, you would say, okay, well, this point 40 and this point negative 40, they would be like here and here, and then it just really starts to split apart from each other. And so the domain should be written in two separate parts. You could say something like x is greater than or equal to 4, and x is less than or equal to negative 4. And then you could say, well, what would happen with the range? Well, it's going to go up and down forever. So you could say y would be all real numbers. And what do you notice about very large values of x? If you're to describe this, I would say something along this line. You could say they remain just larger, slightly larger than values of y. So therefore, there's some sort of asymptote behavior that's happening, and we can start to explore that in our upcoming examples. That's just sort of a preview right there. Okay, so question number 1, you can see here's an asymptote drawn in here, and they're saying, okay, let's find out all of these characteristics. I'll tell you what, the very first thing we should do though is we should find out the equation of this hyperbola in general. And actually this example will set us up where the next few examples may even seem a little bit easier after this one here. So we have a center point still, and our center point is at -1, -2, -3, -3, 2. And it's a parabola that's going to, or sorry, it's a hyperbola, sorry, that's opening up and down. So it's in this form of y squared minus x squared equals 1. And we have a vertice here and here. And what we want to do is, if you're thinking about some terms, you can join this right here. And you'll remember that that was called our transverse axis. And then you know that running horizontally is going to be your conjugate axis, but you might be thinking like, well, how long do I go for the conjugate axis? If it's asking me for the length of the conjugate axis, I'm not sure how far to go. So here's what you do. You take a look at your vertice, and you can join it horizontally, until it meets the asymptote. And then from there, you can create a box. And the box that you create, I think Michelson actually has a term for it. He calls it like the fundamental rectangle or something like that. And that's going to tell us the length of the conjugate axis. And that's going to be right here. Okay, so what do we know about this? We know we have a center of -3, 2. And so you could say something like y minus 2 squared minus minus x plus 3 squared equals 1. And then you could say, well, in the same way that we would do an ellipse, we know we're going up and down from the center point, up 4 and down 4. So this would be 16. And we're going left 2 and right 2. So this would be 2 squared, which would be 4. And that would be our equation right there. The slopes of the asymptotes, well, from our center point to the corner here, you're going up 1, 2, 3, 4, and running 2. So you'd have a rise of 4 and a run of 2. So the slopes of your asymptotes are going in both directions. They're going, and they're symmetrical to each other. So you could say it would be plus or minus 4 over 2, but probably you want to reduce that and say plus or minus 2 over 1. Include the plus or minus because there are two asymptotes happening there. Now, in terms of something to do with the form of y equals mx plus b, if they want the full-on equations of the asymptotes, we can do that as well. Let's do that down here. Because that's going to take a tiny bit longer, let's just quickly answer. The length of the transverse axis is going to be 8 units. And the length of the conjugate axis is going to be 4 units. So the equations of the asymptotes, so let's do them one at a time. So for a positive slope, you could say y equals 2x plus b. And then over here, you could have y equals negative 2x plus b. And what you want to do is you want to sub in a point that you know is on the line, on the asymptote. Now, for this particular case, it looks like for our positive slope, we can actually probably see what the y-intercept is right here. It looks like that's for sure at 6, 7, 8. So it looks like we could probably actually just say something like y equals 2x plus 8 because that's given to us. But if we didn't have that given to us, then you could sub in any point on the line and you could find out what it would be. Let's do that for the second example right here, just because sure, we can see that we can find out our y-intercept pretty easily. But if you didn't know that, but we know that it crosses through the point -3, 2, then you could say something like, okay, sub -3, 2, and you could say 2 equals -2 times -3 plus b, and then you could get from that -6, positive 6, so you would subtract 6 onto the other side, -4, and so then you could say that means that our other equation would be y, you could say y equals -2x subtract 4. Okay, so that's how you find out the equations of the asymptotes, and that's slightly different from saying the slopes of the asymptotes because they want you to express it in the form of y equals mx plus b. Okay, so we're actually going to back it up. These next examples might seem a little bit easier because you have an origin at 0, 0. So here we have the origin at 0, 0. We're starting with an x, and we're going 4 to the left, and we're going 4 to the right. I did that totally backwards. And we're going up 3 and down 3. We could put in our fundamental rectangle if we want to. I think I just like saying that, the fundamental rectangle. So you know what? Sure, let's draw that in. Okay, and based off of this, it's beginning with an x. And so what you can do is you could draw your asymptotes through the corners of the rectangle. And then from here, you can highlight your vertices and you can do a sketch, and it doesn't need to be more exact than this. Put arrows But as long as you have something like that, that's good enough for what we're looking for. And we could label the vertices. This would be 4, 0, and this would be -4, 0. And we have our asymptote lines drawn in, and that looks great. Okay, if they want to say what the equations of the slope are and all that stuff, we could ask you that. We worked on that last example, so I think we'll see it again coming up. Okay, example 3. So this is more a terminology question, I think, than anything else. I think it's quite similar to example 2. Write the equation of the hyperbola and its asymptotes with center 0, 0. So let's do a sketch. So center 0, 0. The transverse axis is vertical and it's 6 units in length. So we would go up 3 and down 3. And the conjugate axis is 8 units. Whoops, so you could draw your box. You have your asymptotes here and here. And our transverse axis means that this one would be an example of where we're opening up and down, because the transverse joins joins the vertices. And so that means we're going to start with a y when we write this out, and you could say something like y squared over 9 minus x squared over 16 equals 1. And I think that answers everything we need for that. It gives us all of the characteristics. We went 3 up, 3 down, 4 right, 4 left. That looks pretty good. It says write the equation of the asymptotes too, maybe. So the equation of the asymptotes, from the center 0, 0, we rise 3 and we run 4. So we could say the equations of the asymptotes would be 3 over 4, plus or minus, because it goes in both directions. And if they want the full-on equation, y equals mx plus b, kind of like what happened here where they want the equation of the asymptotes, not just the slope of the asymptotes, then because it goes through the point 0, 0, we could just say y equals plus or minus 3 over 4x, and that would give us both of them. Okay, example number 4. Find the equation of the hyperbola and the equation of the asymptotes. And this is going to be a very similar question to what you've done with ellipses recently. So you want to reorder it, and you want to put your y's together and you want to put your x's together. And let's complete the square twice. So you would have bracket y squared plus 6y blank blank minus 4 x squared minus 8x, because we've factored out a 4, blank blank, equals 59. Then we can invite in positive 9, negative 9. And here with the 8, half of 8 is 4, so invite positive 16, negative 16. And then we want to figure out, well, this 9 needs to come out. So negative 9 is going to be on the outside over here. And here, negative 4 times negative 16 need to be times by each other. So positive 64 would be coming out right over there. Okay, so based off of this, we now have some perfect square trinomials that we could factor. You'd have y plus 3 squared minus 4x minus 4 squared. And then we would get something that would be saying plus 55 equals 59. So we want to subtract 55 onto the other side. And then you're going to want to do 59 minus 55 to create a 4. So I'm just going to continue this on over here. So you could say something like y plus 3 squared minus 4x minus 4 squared equals 4. divided by 4 because we want it to be in the form where it's all equal to 1. And then you could say something like y plus 3 squared over 4 minus x minus 4 squared over 1. You don't need to write the 1 if you don't want to. All equals 1. And this would be the equation in graphing form to be able to see what this hyperbola is going to look like. So let's think about this. You know that it's going to be pointing up and pointing down. You know that it has a center point of 4 for x and down 3 for y. So at 4, negative 3, you would have a center point right there. And then your y's are going up 2 and down 2. And your x's are going left 1 and right 1. So we have a small fundamental rectangle. Okay, there we go. And then I'm just going to draw in some asymptotes that go through the diagonals of that. And then from right here and right here, we could sketch in with some arrows what our hyperbola would look like, knowing it's going up and down because we were beginning with a y squared instead of with an x squared. Now it's asking us, it says find the equation of the hyperbola, and it also says find the equation of the asymptotes. And so then to find the equation of the asymptotes, we should just look at this a little bit more. So we know that the asymptotes would have a slope of 2 over 1, and there's going to be two cases. So you could say y equals 2x plus b and y equals negative 2x plus b. And we know that in both cases, they pass through the center point, and the center point was 4, negative 3. And so if you want to find your b value, you could always just say, let's sub in negative 3 for y, 4 for x, and you would get negative 11 equals b. So you could say y equals 2x minus 11 for one of the cases. And then for your second case, again, we can sub in the center point. So you could say negative 3 equals negative 2 times 4 plus b. And so then you could say something like y equals 2x plus 5. Okay, so those are the two equations that you have for your asymptotes. Oh, sorry, I think I forgot the negative sign right there. Okay. Now, once again, we have to take a look at the foci again, and once again, there's a long proof, and I'm disappointed that we're not going through the proof. Maybe it's something that we should look at some point. But on page 376 of Michelson, there's a really nice proof that goes through how to be able to find this out. But basically, for the foci for a hyperbola, it's on the outside of the vertices, and it creates this same idea of the u and the v, and if you take a look at what happens with that, the u value subtract the v value is going to be equal to 2a values, and if you wanted to come up with a clean formula for that, eventually you get c squared is going to be equal to a squared plus b squared, where once again we can say something where c is talking about the foci, a is talking about, I guess in this case we won't say major axis because that doesn't exist, so we'll say this is going to be the transverse axis, the axis that joins the vertices together, and then b, the conjugate axis. Okay, and once again, you'll be saying, hey, do we have access to this formula? You will for your assessments, and so just know that c squared equals a squared plus b squared for our hyperbolas. Okay, so find the equation of the hyperbola with center 3, negative 3, 4, vertex of negative 1, 4, and a focus of 3, 4. Okay, let's sketch this out just so we can get our head around everything. So we have a center of negative 3, 4, and we have a vertex of negative 1, 4, and we have a focus of 3, 4. Okay, so a couple things that would come right away from that. You could say what's happening to the left of this as well, but we know that if from the center to the vertex is a distance of just 2 units, then we know that we would have something with a transverse axis that would be those 2 units plus another 2 units, so it would be a total of 4 units. We also know that because our vertices are happening to the right and to the left, that they would be opening outwards. And that means that we would have something in the form of x squared minus y squared equals 1. So let's begin by plotting what we would say would be the center of the, or sorry, writing out the center of the circle. We could say x plus 3 squared minus y subtract 4 squared equals 1. And then based off of that, we could think about, we've gone 2 to the right to go from the center point out to the vertex. And so 2 squared would give us 4. So we know that we would have a 4 right here. And now we're actually almost done. We just need to find out what would go underneath the y values. And using the formula that we have, where we could say c squared equals a squared plus b squared, we know that for the focus, moving from the center all the way to the focus was moving 6 units to the right. So 6 squared would give us 36, or we'll say 6 squared to begin with. Our a squared value was 2 squared, and we want to find out what our b squared value is going to be. So we get 36 equals 4 plus b squared. So that means that 32 is going to equal our b squared value, which means we could write 32 right there. If you square root it, you'd be finding out what b is, but then you'd have to square it again to figure out what you'd have to put in for our graphing form. So this is our best way of being able to express it. And that would be how you could find out something like that. So kind of interesting that you can use the focus to be able to find a lot more information. And then question 6, I think I need to check this, but I'm pretty sure that when I was looking through this, I think that this is a typo. And if we take a look at, if you look at this, and they're saying that, find the equation of the hyperbola if the difference between xy and the points negative 1, 3 and 1, 7 is always 6 for every point xy. This question on its own wouldn't make sense. If you're to sketch that out, we need to have something that would line up. So I think that we are going to rename it so it's the point 1, negative 3. And if you do something like that, then the 1, negative 3 and the 1, 7, if we did a mini sketch of that, is going to look a whole lot better, because you'd have 1, negative 3. Okay, and then if we had 1, 7, okay, then that's going to look much better. Now they're saying find the equation of the hyperbola if the difference between any point and those 2 points is always 6. Well, by definition, if it's always going to equal 6 for those 2 points, then these two are our foci points, because it's always equal to a consistent value. And so if we average out that, we could get the point from 7 to negative 3 right here. This would be at 1, 2. This point right here would have to be our center. And it also means that we know that we're going to have our transverse axis is going up and down. And we can start to write out parts of the equation now. So if we have a center of 1, 2, and we're opening up and down, you'd have something here, you'd have something here. You would be in the form of y subtract 2 squared subtract x minus 1 squared equals 1. And then we need to know what goes on the denominators for this. So let's see what we know in the form of c squared equals a squared plus b squared. Well, we know our c value is 6, and if we can say something to do with our c value being 6, then we should be able to sub that in here. And we also we know something else too. So wait a minute, our c value isn't 6. What am I saying? If we have right here a y value of 7 and a y value of -3, then the distance of our foci is a total of 10. And so if you split that in half, then that would be 5, which means our c value here is going to be 5. So we could say that would be 5 squared. And then we know that the distance to every point is going to be 6. So let's use the distance of our vertices. If that's a distance of 6, then we know that that would be 3, that would be 3, which means that our a value would be 3 squared, and we could find out what our b value is. And that would be 25 equals 9 plus b squared. So b squared is going to equal 16. And so that means that we could now say going up and down was 3 squared, so that would be a 9 right here. And going left and right would be a b squared value of 16, so we can put that in right here, and we should have the equation for what we need to be able to figure that out. Yeah, that I think that's good. Okay, let's look at a couple extra practice questions. Taking a look at what we have right here. I think most of these you could probably answer pretty quickly here. The equation of the conic that represents a hyperbola with, well, if it has a center of 3 and -2, which of these has a center of 3 and -2? It could be potentially D or potentially A. And then you want to think about where your vertices would be. I guess if you had something at 3, -2, and you're beginning with an X, then you'd be going 5 to the left and 5 to the right. And so if this here was at 3, -2, and you went 5 to the right, you would be at 8, -2, and you went 5 to the left, you'd be at -2, -2. So it's got to be D. Determine the length of the transverse axis. So good refresher, transverse axis would be where we're joining our vertices with this. So if you think about the 1 right here, if you have that and you square root it, you get 1, and you go 1 to the left, 1 to the right, then you would have a transverse axis of a full length of 2. And then to convert to general form, this would be timesing by a common value. Let's do this one quickly. So we could say let's times everything by a 6. And if you do that, you eliminate the denominator, so then you could have 3 x squared minus 6x plus 9 minus 2 y squared plus 4y plus 4 equals 6. And we can start to expand this. 3x squared minus 18x plus 27 minus 2y squared plus 8y. Nope, minus 8y. minus 8 equals 6. Let's actually subtract 6 onto the other side, equals 0. And then we can join some like terms. We'd have 3x squared minus 2y squared minus 18x minus 8y. And then here we have a 27, subtract 14. That'd leave us with plus 13. And that would be minus 2 minus 18. That looks great. Looks like it would be A right there. Okay, taking a look at the homework, I just want to see what we have, make sure it seems reasonable. Okay, we will say, okay, let's trim this down. So we'll say it's going to be numbers 1 to 3. Nope. 1 to 2. We'll go 3 odd. 4 and 5. And we'll keep 10. Okay, so those are your questions. Don't worry about multiple choice question 8. We can look at some multiple choice questions down the road. But that's it for conics, and that's it for Hyperbola. So thanks for joining.